So this part of 7.3 is for the washer method for finding for determining volumes of surfaces of revolution. And so we're still working with this essential question of how do integrals explain physical quantities. So just to kind of prepare you for some of the computational stuff, we'll take a little look at order of operations. So if we look at this 5 squared minus 2 squared, that is not 3 squared, that is actually 21. So likewise, that's not 5 squared, 95, and this is not 11 squared, this is 319. So these order of operations are going to become important today. If we add the grouping symbols, now that is 3 squared. And this is 5 squared if we add grouping symbols. And if we put grouping symbols on this one, then that would be 11 squared. But we have to kind of acknowledge that those are not processes that give us equal values. We're going to not be doing this today. This is what we're going to be doing, is keeping these squared, these powers with their numbers. So in the situation where we have an enclosed shaded region that we're revolving about a line, and that region doesn't touch the line, then we develop a hole through the middle of the solid. And so if that's the case, then as we're rotating about the x-axis, we have this outer radius squared minus this inner radius squared. And so this is kind of a modeling of that scenario. So here's our enclosed region, and we're going to revolve that around the x-axis. And as we do that, you can see that we create this surface where the outer surface is that orange and the inner surface is the purple. And since that enclosed region didn't touch the axis of revolution, we've got that hole through the center. So we're still going to slice this and create basically a disc with a hole in it, which is why we call it a washer. So revolving it about the x-axis then, just to kind of bring in the topics from the disk section. That's going to be a dx problem, and around the y-axis is going to be a dy problem. So let's take a look at revolving this about the y-axis. So if we do that, then we spin it, it looks like that, and so we get this kind of cone head or nose cone, so to speak. And then if you can see this light line here, we've got a cylinder that's kind of drilled out of the center, so this whole inside here is open. And we could do this by using our washer method on the nose cone, and then using geometry and subtract off the inner cone if we wanted to. But really, to do this in the least amount of steps, we use that washer approach with our integration. So we can see that if I back up here, we have that horizontal slice right here, and when we spin that, it becomes this washer. So relative to the axis of rotation, the outer surface is this parabola, and the inner surface is the line. So that being the case, then we create, you can call it a washer, you can call it a donut, but its area is going to be pi big R squared, that's the outer radius, minus pi little r squared, which is the inner radius. And then if we multiply that times the thickness, we can get the volume of that washer. And that's basically what we integrate then. Since this is revolved about the y-axis, this is a dy problem. That just means we need to rearrange these to get them in terms of y. So our outer radius, our parabola, we'll rearrange that in just a second. Our inner radius is our line. And so solving this to get this in terms of y, we're going to square root both sides. So there's our outer radius. And then getting the line in terms of y, we'll divide each side by 2. and we get y over 2. So setting up the integral then, we're going to have the integral for the volume. So we've got pi times the integral, and we're going to stack these washers from down here vertically all the way up to here, so from 0 to 4. And then our big radius is going to be the square root of y, and then we have to square that, so that's this. And that's our outside radius, and then our inner radius is the y over 2, so that's the little r, and we have to square that. So simplifying that, that's just y, and this is y squared over 4. And we can integrate this by hand. So we've got the antiderivative of y is y squared over 2. And then the antiderivative of this, we'll get the quarter out front, and then this is y cubed over 3. And then we can plug in the 4 and the 0, and we'll gloss over the fractions at this point because you can handle the fractions. Simplified this to be y cubed over 12, and then putting in the 4 gets us 8 minus 16 thirds. And again, putting in the 0 just gets us 0, so that's 8 pi over 3. So that would be the volume of this this cone-shaped, this nose cone shaped with this geometric cone shaped out of the center. The other thing we see that's really common is up until now we've revolved things about either the x or the y axis, but sometimes we revolve it about a line that's parallel to an axis. So in this case, I have two parabolas here. This parabola x squared is this orange curve. We're just looking at it in the first quadrant. And then this 4x minus x squared, this parabola is the purple. We're just, again, looking at half of it, basically. And if I want to revolve this about the line y equals 5, then as I spin this, it's going to create this hole through the center of the shape right there. So as we watch,
for this washer method, we are going to take the region bounded by two parabolas. So this orange parabola is the region, or the function x squared, and this purple parabola here is the function 4x minus x squared. So that creates an enclosed region, and we're going to take that enclosed region, here it is in 3D, and revolve it about the line y equals 5. So we're going to be able to create something that's got a hole through the center here. So as we revolve this around the line y equals 5, we get this shape that kind of looks like a flat, almost like a skittle with a hole through the middle. So you notice the orange outside has this curved shape, and this purple inside actually has the same curved shape. So looking at this, as we revolve around, so we can see this from the front. That's that curved parabolic shape. And maybe see it from the edge. We can see that that shape has a curve on the outside coming up to the flat spot where the hole is through the middle. And then we have a curve on the inside as well. That's the purple shape on the inside. And so if we tip it backwards to the other side, we can see the purple inside. Let's see if I can get the back side. There we go. There's the back side. So there's your purple back side that's sloping inwards towards that center hole. That's what that 3D shape looks like.
So setting up the the washer for this, and since we're revolving it about y equals 5, which is parallel to the x-axis, this is a dx problem. So here's our rectangle that when spun will create that washer. So if you notice, again, everything is measured from the axis of revolution. So if this is where we're rotating about, the outside, the big R, the outside surface is orange. So that's your big R. from here to there. And then the inside radius is your little r, and that's from the axis of revolution to the purple surface. And so the tricky thing about a line parallel to an axis is that these functions are relative to the origin here. And so when we have to write the expressions for big R and little r, we have to remember that the function itself, like this is x squared, that's with respect to this origin here. So x squared is really this measurement right here. So the radius of curvature, or the radius of rotation then, is really 5 minus x squared. And likewise, for the inside surface, the purple surface is 4 minus x squared relative to the origin. So this little radius here is really 5 minus this. So our outside radius is 5 minus x squared. It's that distance there. Our inside radius is 5 minus this, 4 minus x squared. 4x minus x squared, excuse me. So we have these two radii of rotation, and that's what we have to put into the integration expression. So we're going to stack these washers from here to here. So we're going to start at 0 and go to 2. And I put the pi on the inside, but we can bring the pi to the outside too. And our big radius is 5 minus x squared, and then we have to square that. That's a really common thing to forget. So this is big R squared minus little r, which is going to be 5 minus the quantity 4x minus x squared, and we have to square that as well. And then our dx are different, our dummy variable there. So I think what I do here is I suggest that you pull the pi out, and then this is a lot of foiling. So this is definitely a calculator type of question. So we're going to go ahead and I'm going to reintroduce that usage of the vars key right here. So in order to use that vars key, I'm putting big R into y1, and then I'm going to put little r into y2. And then I can just pull those into my integration expression. So now I can go back to my calculator screen and do a math 9. So I'm going to go ahead and do a math 9, get my fn int, and I'll go from 0 to 2. And then instead of having to type in the whole complicated radius expression, I'm just going to grab y1 and y2 out of vars. So I'm going to go into vars and go into yvars and grab a function. And I'm going to, y1 was my big R, so I'm going to grab that first, and I'm going to square it. And then I'm going to subtract the little r, so I have to go back into vars again and grab y2. And then I'm going to square that. And so that gets a much cleaner look on your calculator screen. You don't have to worry so much about all those brackets and stuff. And then I put in my dummy variable dx and then hit enter. And remember, this integration was done without the pi. So if I multiply the pi in, we're going to get something in about the 50s. So about 50.265. A lot of times though, what you really want to do, and here's the calculator syntax if you want that. What you really want to do is answer in terms of pi. So you would leave the answer as 16 pi cubic units. So at this point you should be able to work on the volume washer homework. We still have one more day in section 7.3, so if you're looking to take a Blackboard quiz, wait until the next class.